Hello everybody, this is Mr. Strager, and welcome back to Big Ideas Unit 3. Today we are looking at section 3.2. Now, last section we talked about whether or not things were functions, and that's kind of setting us up for the rest of the unit. The rest of the unit is figuring out if something is a function, but then we also want to figure out some more specific things. One of those specific things is figuring out if a function is a linear equation. When I say the word linear, what words come to mind? If you said line, you're absolutely right. Linear just means in a straight line. Now, we might have dealt with an equation for straight lines in the past, so this may seem a little bit familiar. In fact, I want you to see if you can guess what the equation is as I'm writing it. The equation of a straight line looks like this. Y equals m times x plus b. This is the equation for a linear, this is a linear equation. A linear equation in two variables will always be written like this, or can be rewritten like this. As a reminder from years past, normally we would talk more in depth about the slope, which is m. So m is your slope of your line, and b, which is your y-intercept. But not today. That's not really the focus. Today's focus is just talking about our x's, or our inputs, and our y's, which are our outputs. The goal here is to be able to determine, hey, is something a linear equation or not? To figure out how to go through that pattern, as well as to figure out a little bit more about the domains. So a linear equation in two variables is anything that can be rewritten like this. A linear function is a little bit more specific. It's a function whose graph is a non-vertical straight line. A function whose graph is a non-vertical straight line. Well, what do I mean by that? Let's say for a minute that we have a coordinate grid. We're going to call a Cartesian plane in the future. If I have a line that is straight and is non-vertical, this is a linear function. Anytime that line stops being straight, there we go, then it stops being a linear function. So if I have a line that looks like this is no longer a linear function because it's not a straight line. But there was one other little caveat there. What if my line looks like this? What if it just goes up and down? I mean, that's still a straight line, right? Why can't that be a linear function? Well, the key word is the word function. Let's say for a minute that I labeled my x-axis. 0, 1, 2, 3, and so on and so forth. Remember from last section, we talked about a vertical line test. If you can draw a vertical line through all the points on your graph, and each line only passes through your graph a maximum of one time, it's a function. But if that vertical line can pass through multiple points, it's no longer a function. Here, the vertical line passes through the entire line that we drew. So it is super not a function. You can also think about it like this. our inputs are down here, right? So our input for this line would be 2. But what are its outputs? Well, 2 goes to 1, for instance. But it also goes to 2 and to 3. In each of these places, 2 has an output. So not only does 2 not go to just one output, it goes to an infinite number of outputs. So it's super not a function. There is one more piece of this definition that's kind of important. A linear function is a function whose graph is a non-vertical straight line, but it also has a constant rate of change. It has to have a constant rate of change, meaning that whenever you go over 1 and up 1, that pattern repeats every single time. Or if you go down 3 and over 4, that pattern keeps repeating. In this graph, which I drew semi-poorly, we can take a look at some of the points that fall right on these crosses. So let's pretend for a second that this line was perfectly drawn, and our dots were looking like this. You can see if something has a constant rate of change by counting how much to the left or right you have to go to get to the next point, and how much up or down you have to go to get to the next point, and see if that pattern continues. So in this case, I'm going 2 to the right and 1 up. Our line has a constant rate of change if this pattern keeps continuing. So I went 2 to the right here as well, and 1 up to get to the next point. And then I went 2 to the right again, and 1 up to get to the next point. Since this pattern continues forever, we have a linear function. It has a constant rate of change. The rate of change is 2 to the right and 1 up. If you look at a graph like this, I think it's pretty clear to see that we won't have a constant rate of change. Let me put a couple of points on as an example. If you were comparing these points, let's take a look and see. You go 1 to the right and 1 up. You go 1 to the right and 1 up. Things are looking good. You go 1 to the right and 2 up. So it's no longer a constant rate of change. The rate of change is different between each point. So those are the aspects of a linear function. There is just one more definition we're going to talk about before we do a couple of examples, and then we'll go back to the definitions in a little bit. But that is a nonlinear function. Well, if a linear function is a function whose graph is a non-vertical straight line, a nonlinear function is a function whose graph is not a nonlinear straight line. A function whose graph is not a non-vertical straight line. So it's anything that has a curve in it or anything that is a vertical straight line. Well, what does that mean for the rate of change? Well, it means it does not have a constant rate of change. So in the last section, our goal was to determine if something was a function or not a function. For the purposes of this section, everything in here is a function. We just want to figure out if it's linear or nonlinear. So let's flip to page 68 and try some of these out. I want us to try out questions 1, 2, 3, and 4. Questions 1 and 2 should be pretty easy to determine if it's linear or nonlinear, but questions 3 and 4, we might have to think back about that constant rate of change. I want you to pause the video here, see if you can get them all, and come back once you've tried them all out. How we do? Let's take a look at why these are the way they are. So this one is nonlinear, and it asks you to explain your answer. You could explain it a couple of different ways. You can even just simply say it's not a straight line. But I'm going to explain it in terms of the rate of change. Let's say I'm looking at 2 points. I'm looking at this point right here, this point right here. The first one, we go to the right one and up one. The second one, we have to go to the right 3 and up one. So immediately we say it's nonlinear because it doesn't have a constant rate of change. But what about example number 2? There are 3 places where the line crosses through the grid marks exactly that we can use to determine this. We have to go, starting from one point, to the right 4 and up 1 to get to the next point. And if we do it again, we see we go to the right 4 and up 1 once again. It's linear because the way it's changing is the same each time. It has a constant rate of change. Now, it might have been a little bit confusing to try out questions 3 and 4, but let's take a look. Again, the goal is to figure out if there is a constant rate of change. Well, how do we do that? Let's see how much our x's are changing each time and how much our y's are changing each time. So if I go from x is 1 to x is 2, we're adding 1. 2 to 3, we're adding 1. 3 to 4, we're adding 1. So it looks like our x's are constant because the rule is that we just add 1 each time. But it's not enough to say that just one variable is constant. Both variables need to be constant. If only one variable is constant, like we just said, oh, our y is constant, we're just going up each time, it must be linear, that would be incorrect. So we have to check both variables. How do we get from -1 to 2? Well, by adding 3. How do we get from 2 to 5? By adding 3. And how do we get from 5 to 8? By adding 3. Our x's are going up by 1 each time, our y's are going up by 3 each time. It's linear because these are constant. It never changes. Not the same can be said for number 4. Here, from -1 to 0, we add 1. From 0 to 1, we add 1. And from 1 to 2, we add 1. But in our y's, to go from 0 to -1, we're subtracting 1. To go from -1 to 0, we're adding 1. And to go from 0 to 3, we're adding 3. It is nonlinear because it keeps on changing. So let's flip back to our notes for a second, because we've talked a lot about graphs and we've talked about points. We now need to transition to talking about equations and figuring out if something is a linear equation. As a reminder, a linear equation is anything that can be rewritten in this form. It's a little hard to see what can be rewritten in this form, though, so let's take a look at some examples. I want you to split our notes section into 2 pieces. On the left side, we will have linear, and on the right side, we will have nonlinear. So as a reminder, we want everything to be able to be rewritten as y equals mx plus b in order for it to be linear. So let's think about this one. Is this linear? Well, yes. M is -1, b is 3. It can be rewritten in this way. That's perfect. What about something like this? Y minus 1 equals 3/4 x. This one's a little bit trickier to see, but it can still be rewritten into that y equals mx plus b form. All we would need to do is add 1 to both sides, and you'd end up with y equals 3/4 x plus 1. A couple of tricky ones are these. For instance, if I have y equals, let's say, x minus 1. Now you might be tempted to say, oh, wait a second, it's not linear anymore. But remember, anytime your x is by itself with nothing in front of it, that's the same as saying 1x. So this is linear. Another tricky one is this. What if I don't have an x at all? What if I just have a number? Turns out it can still be linear because this is the same as y equals 0x plus 3. There are a lot of ways to write linear equations. Your main goal should be to figure out if you can rewrite things in this form. However, there are some things that can help us immediately say, nope, not linear, don't even need to rewrite it. If we take a look at things that are nonlinear, there are certain traits that tend to pop out. One of the most common ones you'll see is anytime one of your variables has an exponent, like x squared or y cubed or x to the 27th power, these immediately let us know this is nonlinear. It'll make a curved line, as we'll see next semester. The same can be said if you have a square root, because a square root is the opposite of squaring, so it's basically going to end up with a very similar shape. The other type of exponent you might see is your number with a variable in the exponent. Still not linear anytime there's an exponent on one of your variables or involving one of your variables. Some of the harder ones to look at, though, will be things like this. In fact, these might be a little tricky to figure out why. Absolute value is considered not linear. We'll take a look more at what this graph will look like later on in the unit, but the idea is you'll basically end up with a V shape. And because the rate of change is not constant, it is not linear. The last one is going to be the trickiest one. But anytime one of your variables is in the denominator of a fraction, it is non-linear. This only works if it's in the denominator of a fraction. Something that would be linear is something like y equals x over 5. That's totally fine. Anytime a variable is in the denominator of a fraction, and you cannot get it into y equals mx plus b form, it is non-linear. These will be very tricky to see at first, but the examples I'm going to give will be a little bit basic starting off, and when we go through the unit, we'll get better and better at it. So let's flip back to page 68 and try some of these out. For numbers 5 and 6, I want you to write out if it is linear or nonlinear. You don't need to rewrite the equations, but I do want you to point out why it's linear or nonlinear. Pause the video and try these two out. So, let's take a look. Question number 5 is linear, because you can rewrite it into slope-intercept form, y equals mx plus b. You don't need to actually do this part on your paper to show that it's linear, you just need to say it can be rewritten. But if you did want to rewrite it, it would look like this. What about number 6? Well, on number 6, we take a look and we see there's an exponent. So that immediately tells us it is nonlinear. The very last piece of our notes is determining these complex sounding words called discrete and continuous. We actually unknowingly have already talked about discrete and continuous. However, we haven't actually formalized them as these words. If we flip back a couple of pages to our 3.1 notes, we actually see examples of discrete and continuous graphs. Basically, a discrete graph is when you have a bunch of points that mark out all the places the function is at. A continuous graph is any time you have a line or a curve. here, we're talking about discrete domains and continuous domains. So the way we define it is this. A discrete domain is a set of input values, which as a reminder are x values, that consists, whoops, sorry, my pen just ran out, consists of only certain numbers. You can think of this as being a bunch of dots. So anytime you have like dots, 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 and they make a graph, that is a discrete domain. A continuous domain is similar, but instead of being dots, it's when you end up with lines. So a continuous domain is a set of, once again, input values. Oops. Our input x values that consists of all numbers in an interval. This is any time you end up with a line or a curve as your graph. When we write out these domains, we have to write them out differently, just like we did in 3.1, because they're so different. With this one, you can list off all the places that x can be, just by listing off the numbers. With a continuous domain, you would need to list off the interval to show that x is anywhere in between them. Numbers 7 and 8 on page 68 talk about these. We want to first find the domain of the function and then determine if it is discrete or continuous. But to be honest, you could probably do it backwards if you wanted to as well, because it's so easy to find out if something is discrete or continuous. Continuous just means it is a line. Discrete means that it's a bunch of dots. Here we have a line, so it is continuous. Here we have a bunch of dots, so it's discrete. The way we write out the domains for both of these are a little bit different. Let's actually start on number 8 because it's easier. A discrete domain requires you to list off all the places x can be. So right here, x is at 1. Right here, the x value is 2. And right here, the x value is 3. We don't care about the y value because that's the range, and we're just asked to find the domain of the function. So the domain is 1, 2, and 3. For a continuous function, your goal is to list off an interval, or a compound inequality, where x can be. To do that, find the most to the left x can be, and the most to the right x can be. To the left, x could be 1. To the right, x could be 5, and our line is everything in between. So x is everywhere between 1 and 5. We have to ask ourselves, could x be 1 or 5? It can be because these are closed circles, and just like last unit, if you have closed circles, your inequality symbols should have bars underneath. That's all for lesson 3.2. Thank you so much, everybody. Have a spectacular rest of your day.